Okay, confidence intervals with a sample standard deviation. This is the second type of confidence interval that we're going to cover. In the real world, when using a sample to estimate a population parameter, it's very unlikely that the population standard deviation will be available. If we had the population parameters like the mean and the standard deviation, why would we need to sample in the first place? So the reason why we look at those examples when we have the population standard deviation as in example 1 and example 2 is basically to understand the mathematics. And after we get a handle on the mathematics, we move on to what really happens in the real world. In these cases, we use the sample standard deviation S for estimating the population standard deviation sigma. It all started when chemist W.S. Gossett worked for Guinness in 1908. He discovered a new statistic that he called the t-score statistic, as opposed to the z-score statistic, while attempting to make accurate conclusions about the population of beer using only small samples. Now, he didn't want to contaminate the entire population of beer, so he used tiny samples of beer. And in using those small samples, he attempted to estimate what the true population parameters regarding the beer were. He found that the t-score statistic was not normally distributed like z-scores. The new distribution became known as the t-distribution. We use the t-distribution when constructing a confidence interval for the mean of the population when the population standard deviation sigma is not known and is estimated by the sample standard deviation S. So in this second type of problem, sigma will not be provided to you. Rather, the sample standard deviation S is going to be provided to you. So let's look at a little bit of what the t-distribution looks like. It's similar to the normal distribution. It is bell-shaped and it never touches the horizontal axis. The area under the t-curve is 100% as with the normal curve. Small samples make the t-distribution more dispersed than the normal distribution. It's lower and flatter. As the sample size increases, the value of the sample standard deviation S gets closer to sigma and the t-distribution approaches the standard normal distribution. And here's a picture. The normal curve is what we know and love. It's in brown here. It's that bell curve that's the tallest here. The t-curve is in gray right below it, and then we have another t-curve that's dotted right below it. The t-curve changes sizes as sample size changes. So when sample size is small, the t-curve is flat and kind of squatty. And as the sample size increases, the t-curve gets taller, and eventually as the sample size gets big, the t-curve basically approaches exactly what the normal curve looks like. Okay, we're going to look at the three types of confidence intervals, the 90%, the 95%, and the 99% for the t-distribution, basically when handling cases when we don't have the population standard deviation. For a 90% confidence interval, the area to the left of the positive t-score, which is right here, area to the left of this score is 95%. So we have the middle 90%, which is associated with a 90% confidence interval, and then we have this bottom 5% in the left tail. So the entire area to the left of this t-score is basically t subscript 95. T subscript 95. The area to the left is 95%, so we refer to the t-score as t sub 95. If we do the same idea with the 95% confidence interval, all the area to the left of this t-score right here is 97.5%. So for a 95% confidence interval, the area to the left of this t-score is 97.5%, and we refer to this t-score as t sub 97.5. And the same for a 99% confidence interval. The area to the left of this t-score is 99.5%, so we refer to this t-score as t sub 99.5. So those are 3 things to keep in mind as we go forward with these problems. Really good things to put on note sheets that you'll eventually be taking to the final exam, because it's not obvious that you'll be using, when asked to construct a 90% confidence interval, it's sometimes hard to remember that you're using the t sub 95% t-score. When constructing a 95% confidence interval, you're going to be using the t sub 97.5% t-score, and constructing a 99% confidence interval, you're using the t sub 99.5% t-score. Now, where this comes into play is the use of a chart that should be part of your notes this lecture. We use the t-distribution to help us build confidence intervals for sample means when the population standard deviation is unknown. Okay, the formulas. When dealing with a 90% confidence interval, it's a very similar formula as we had for the population standard deviation. Note that instead of sigma, we put an S in the numerator. But also notice that instead of the negative 1.65 and positive 1.65, we have this t 95%, t sub 95%, and t sub 95%. And you may wonder, well, where do those values come from? They're going to come from a chart, and we're going to get to that chart in a second. For a 95% confidence interval, the formula changes only slightly. The t-score is a t sub 97.5% and t sub 97.5%. So we had said before, a 90% confidence interval, you're going to use the t sub 95%. A 95% confidence interval, you're going to use the t sub 97.5%. And for a 99% confidence interval, you're going to use the t sub 99.5% confidence, 99.5% t-score. So again, 3 important formulas that should be put on a note sheet for use on your final exam. Okay, if you go to the chart that was provided in the handout for this lecture, it should be the last page. The part that we're concerned with is the part that says 4 confidence intervals. And there are a series of columns, and it's our job to understand what each of these columns mean and how to read this table. T 95%, 97.5%, and 99.5% change based on the size of the sample. So in these problems, it's going to become critical to know the size of the sample in order to figure out what the t-score is that we should be using in the formula. We're never going to be using the 2 columns labeled t subscript 0.1% and t subscript 99%. We're not going to be using these 2 columns in constructing our confidence intervals, so you don't have to worry about them. We're not going to be using the t 0.5%, the t 5%, or the t 2.5% either. The parts that are important for this topic for confidence intervals are the t 99.5% column, the t 95% column, and the t 97.5% column. The degrees of freedom, symbolized by df on the table, is found by taking the sample size minus 1. So if your sample size is 10, degrees of freedom is 9, and then you would go to the row labeled 9. If your sample size was 8, degrees of freedom would be 7, so you go to the column labeled 7. Okay, now if we want to find the value, the t-score for a 90% confidence interval, recall that for a 90% confidence interval we have to use the column labeled t subscript 95. So we go over here, t subscript 95, and if we're using a sample size of 10, we go down to the degrees of freedom labeled 9, and that's where the t-score 1.83 comes from. So that 1.83 now becomes part of our formula. So now you can see how this entire chart is used to populate the formula based on the sample size and based on the confidence level.